great to have Julia speaking to us again. Julia is the Manuel Blum Professor of Computer Science, right? And is working, has done a lot of work in computer science and also combinatorics, and obviously talks every year about something fairly different. But actually, this may be fairly different than I'm trying to think of fairly different from the previous. Some graph spanners before, I think. But okay, so happy to hear what she has to tell us today.
Thanks, Nadim. So now Matty wisely avoids trying to say my last name. Okay, so this talk has a long.
Last year, I did not improve.
This talk has a long title. It's called "Fully Dynamic Algorithms for Graph Spanners via Low Diameter Outer Decomposition." It's based on joint work with Muraf Parter, and in fact, this talk has two parts. The first part is graph spanners, and the second part is low diameter outer decomposition, and in fact, there is very little overlap between the two parts. So I'm going to start with graph spanners, and I'm going to start with the motivation. So what are graph spanners, and why are we interested in them? And one of the main reasons is that there is this really important paradigm that can be used to speed up various algorithms, and it's a graph sparsification paradigm. So what's the idea? So suppose we want to solve some problem on some graph, and maybe this graph is pretty dense. So in order to get a fast algorithm, instead of solving the problem directly on this big graph, what we can first do is compute a subgraph of this graph that is hopefully much sparser, but it approximately preserves the important properties of the original graph. Now, which important properties? It really depends on what you want to solve. So on the problem that you want to solve, so it could be cuts, it could be flows, it could be distances between pairs of vertices, and so on. And then, instead of solving the problem on the original graph G, we solve it on H. H is a much smaller graph, so hopefully your algorithm is much faster. So in this way, you can hope to get a faster algorithm. You will also get some hit on the quality of the solution, because usually these properties, they are not preserved exactly, they're preserved approximately, but often this is good enough. So generally, this graph H, this subgraph of G that's sparse and approximately preserves the important properties of G, it's called a sparsifier. But when we talk about distances and the properties that we want to preserve at distances between pairs of vertices, then it's called a spanner. So a spanner is a kind of a sparsifier. So this is one reason to study spanners and more generally sparsifiers. And another reason is that it's just a really natural graph theoretic concept, and it has some really interesting connections with graph theory. And we are going to see one in a bit. So now to a formal definition of a graph spanner. So generally, we assume that we're given some n-vertex undirected graph G with no negative edge lengths. Throughout much of this talk, I'm going to assume that the edge lengths are unit just to make the presentation simpler. It doesn't make much difference, but they can be any edge lengths. And now, what's a k-spanner of G? Generally, it's a sparse subgraph of G that preserves all distances between pairs of vertices of G to the factor k. So for every pair of vertices in the graph G, the distance between them in H should be at most k times their distance in G. And notice that this inequality holds easily in the other direction simply because H is a subgraph of G, so you don't need to worry about this. So this K is called the stretch of the spanner. It's really the approximation factor. And also, it's easy to see that you can even relax this property but get something that's equivalent. So for example, if we can ensure that this inequality holds for every edge that lies in G but not in H. So if for each such edge, the distance between its endpoints in H is at most k times the length of the edge, you'll get the first property as well. This new property is sufficient. And so when you design algorithms for spanners, it's just more convenient to think about the second property, but when you use it, it's more convenient to think about the first property. So the important parameters of the spanner are the stretch k, which is the approximation factor, and the size, which is the number of edges in the graph. So generally, we want to get a good trade-off between the two, the best possible trade-off, and also we want to get very fast algorithms that allow us to construct spanners. So before I go into trade-offs between the stretch and the size of the spanner, what I'm going to do, I'm going to ask a pretty basic graph theoretic question that seems to be completely unrelated. And then we'll see that it's really very closely related to a trade-off of size and stretch of the spanner. So here is a basic graph theoretic question. So suppose I want to construct an n-vertex graph G whose girth is more than k. So what is girth is the length of the shortest cycle, and it's unweighted. So all its lengths are 1, girth is the length of the shortest cycle. So I want to build a graph in which every cycle has length more than k. And I want to build this graph so that I put as many edges as possible into this graph. And the question is, how many edges, what is the largest number of edges can we put in such a graph? So we don't really know, but let's denote this number by m of k. And as we're going to see, this m of k is very closely related to the size trade-off of a spanner. For example, it's easy to show that there is some n-vertex graph G in which every k minus 1 spanner must have at least m of k edges. Let me show you this, it's very quick. So I'm just going to take that graph G whose girth is more than k and that has m of k edges. It exists by definition of m of k. And they claim that if I want to build a k minus 1 spanner of this graph, I have to include every single edge of this graph in the spanner. I can't miss even one. So why? So suppose I miss this edge, but it's a k minus 1 spanner, so it has to contain a path of length at most k minus 1 from u to v, maybe this path. But then we see that G has a cycle of length k, and we said that G has girth more than k, so that's impossible.
Julia, so this only applies for the unweighted.
Yeah, you can do something. I mean, weighted is more general, right? But yeah, like in the other. So this in particular applies to the weighted, and we'll see the other direction also applies to weighted and weighted. Yes. Okay, so bottom line, there are some graphs G in which every k minus 1 spanner must have at least m of k edges. It turns out that the opposite is also true. If you give me any n-vertex graph G, I can build in it a k minus 1 spanner with m of k edges, and it's very easy to do. I'm going to show you how. Yeah, so this is the part where I'm showing for unweighted, but it actually also works for weighted. You just need generally to work with every weight scale separately. Okay, so how we do this? So we're given this k minus 1, we're given this graph G. I want to build k minus 1 spanner. I start with all vertices of G and no edges. And then I look at every edge of G one by one. And when I look at this edge, I decide I'm going to put it into the spanner or not. How I decide? Like this. So if currently in the current spanner, the distance between the two endpoints of this edge is more than k minus 1, I put it in the spanner. If not, I don't put it. That's it. That's the whole algorithm. And it's immediate to see that we get a k minus 1 spanner. Why? Because whenever I don't put the edge in the spanner, I have a path of length at most k minus 1 connecting the two endpoints. And also the fact that the size of this spanner is at most m of k follows from the fact that the girth of the spanner is more than k. Why is the girth more than k? Well, whenever I insert an edge, I make sure to never close the cycle of length at most k. So the girth is more than k, and the size has to be at most m of k. This is just definition of m of k. So going back to this question, in fact, the answer to this question completely determines what's the best possible straight size trade-off of a spanner that we can get. What do we know about this question? So we don't really know the exact answer, but we have a pretty good idea. So first of all, this is like a really nice exercise if you want to try. It's easy to show that if the girth of a graph is more than 2k, then it cannot have more than n to the 1 plus 1 over k edges. Yes?
So just making sure that this is any order I would use, I'd always get the same any order of the vertices. Like so in the algorithm, in the constructive algorithm, I can use different orders of
yeah, you will not get the same spanner.
No, but not the same spanner, but of the same girth.
Yeah, the girth is most k.
Well,
Not the
exactly.
same. Yes, yes. I don't know. Most k. Why exactly?
You make it
No.
fewer edges. Or no?
Yeah, you
No,
might
the
get fewer edges, yeah. Of course.
Okay.
I mean, you might start with a graph whose girth is less than k, right?
Okay.
Okay, so we have like one bound from one side of this m of k. What about the other side? So there is a really famous Erdős-Girth conjecture from 1964 that basically says that this bound is essentially tight. It says that for every k, there is this graph whose girth is at least 2k plus 1 with basically this number of edges. And it's like a really big open problem in graph theory to prove or disprove this conjecture. It has been open for over 60 years. However, if you're not a math person, you're a computer science person, and you're fine with a little bit of approximation, then we sort of know that this is true because it's pretty easy to construct a graph whose worth is at least k minus 1 of the same size. So, from our side, it's sort of resolved, but if you want to get the exact thing, then it's still open. Okay, so now we go back to spanners. So what does it tell us about spanners? So it tells us that for every k, every graph has a 2k minus 1 spanner on number of edges at most n to the 1 plus 1 over k. This is tied under the Euler-Gersh conjecture, and it's close to being tied under existing unconditional bounds. And also, there is an algorithm that constructs a spanner with pretty much the same trade-off, a little bit worse. And its running time is k times m. M is the number of edges in the graph. And usually you should think about this k as being like a constant or polylog n. So essentially this algorithm gives you pretty much the best you can hope for. But there is maybe some little room for improvement, but it's close to the best you can hope for. So, are we done?
Okay, just so tight means it's existential, right? In other words, there exist graphs you can't do better, but some graphs you could do much less.
Oh yeah, it's not graph. Yeah. Obviously, you can get a very sparse graph.
Right.
Yeah, you can have graph with no edges. Okay, so far we talked about the static setting. So somebody gives me a graph, I compute a spanner, we are done. And what I'm going to discuss today is a dynamic setting where the graph changes over time, and as it changes, I have to maintain a good spanner for it. So in the fully dynamic setting, we have an input graph, and it changes over time. And the changes that are allowed, you can delete an edge from a graph or insert an edge into a graph. And each such change, it counts as a single update. So as this graph G changes, we need to maintain a good spanner of the current graph at all times. And now notice, you can even think about it as if at the beginning G has no edges, then somebody starts inserting edges and then maybe deleting and so on. So obviously as G changes, we need to change our spanner H as well. So the spanner H itself is also a dynamic graph. Now, why would we want to study spanners in dynamic graphs? And the reason is the same as for static graphs, because we can use exactly the same idea. If I want to get a fast algorithm for an algorithm for a problem on a dynamic graph, I can do the same thing. I can maintain a sparse spanner or a sparsifier for that graph and then apply the algorithm to the spanner and not the original graph. So as long as I can maintain the spanner efficiently, this is good. And so it's not surprising that many algorithms for dynamic graphs, they build on this paradigm, they use sparsifiers and most specifically spanners. But even more interestingly, there has been this recent trend of trying to design really fast algorithms for basic graph problems on static graphs, graphs that don't change over time. And oftentimes such algorithms, they need to use dynamic algorithms as subroutines. And quite a few of them also build on dynamic spanners and dynamic sparsifiers. And there is one notable example, and this is probably one of the biggest breakthroughs in at least like the last decade in algorithms. It's a very fast algorithm for maximum ST flow. The running time is close to the best possible, close to linear. And this algorithm inside, it uses dynamic spanners. So because we'll be talking about dynamic algorithms for the rest of the talk, I'm going to take a little detour, and I'm going to say a few things that are important to know about dynamic algorithms. So first, how do we measure how fast is our dynamic algorithm? So there is a notion of update time. So what's update time? So every time G changes, an edge is deleted or inserted, I may need to go and update my spanner H, and maybe there are some other data structures that I'm maintaining, and I need to also do something. So the time it takes me to process a single update to G, that's the update time. Now, this can be measured as amortized, so on average, for every update to G, how much time it takes me to update my data structures, or in the worst case. And of course, the worst case model is the more powerful one. In fact, as somebody who uses a lot of these dynamic algorithms as subroutines in whatever I do, I can tell you that if this dynamic algorithm comes with the worst case update time guarantee, it's so much more powerful and so much more convenient to use. And so it's not surprising that there is a major direction in dynamic algorithms recently to design algorithms that work well in the worst case and are amortized. So generally ensuring that you have a low worst case update time is very, very challenging. Just think about it. Like every time the graph changes, you need to make sure you only spend very little time on processing it. It's very hard to do this, to design such algorithms and to prove this. But there is a really neat trick. It doesn't always work, but it works quite often. And this trick is to use an intermediate model called batch update model. So what is this batch update model? So now instead of the edges, the updates coming one by one, they come in batches. And the number of batches is not so huge. It's R, which is going to be like some large constant. But in every batch, there could be any number of the updates, maybe 1 and maybe n. So what happens after every batch BI arrives? We need to process it and produce a spanner that's up to date with respect to the current graph. And the important thing is that the time to process batch BI should be proportional to the size of the BI. So it's sum T times BI. So if BI has many edges, maybe processing time can be longer. If it has only one edge, it will be shorter. Can I just continue for a bit and then I may answer a question? Just to put this into context, if R is 1, so there is just one batch, that's exactly amortized model. If the number of batches is unlimited, but every batch has just one update, it's exactly the worst case model. But here the number of batches is a large constant, and the size of every batch can be anything. So it's an intermediate model between the two. And there is a really cool thing that there is a reduction that says that typically, though not always, if you can get algorithm that works in this batch update model, there is an automatic way to transform it so that it also works in the worst case update model. And you pay a little bit in the update time, so the overhead is like n to the 1 over r. Remember, r is a large constant. So you pay a little bit, but it's not so crazy. And when you work with this batch update model, life is so much easier because you only need to withstand these R attacks, right? A constant number of them, and that's it. So it doesn't always work. By the way, it was formalized by these people. This reduction doesn't always work, but problems that and algorithms that I'm going to talk about today, this reduction does work for them. So just remember when I talk later about some algorithms, and I say you need worst case update time, and it looks very tricky. Well, you only need to do this. This makes life much easier.
What does it mean, a reduction that doesn't always work? I mean, is it like an idea that you can apply, or it's not like a
No, so what
theorem
happens,
that you can plug in?
so what actually happens is that, as often happens in these things, it maintains several data structures, and at every time one of them is up to date.
Okay.
So if you need to maintain a single graph, it maybe, anyway, it works in some settings, not others. You actually, every time you have to go through the reduction and see that it works. And we actually had to do some work to make it work in our setting. It's not completely automatic.
Like, is it the reduction works, but you have to make sure that it actually, the runtime doesn't explode, or that
No, it's more. So for example, just one example, right? So in spanners, you usually want a small recourse. So if your graph changes a little, the spanner should change a little. Now in this reduction, it will maintain like 100 different spanners, and at every time it will say, this is the current, this is the current, this is the current, right? And then from one time to the next, it may switch your spanner completely. That's not good for you, right? For example, this is one example where it wouldn't work. So you need to do a little bit something else. So you need to really get into this reduction and check if it actually works for you. Yes.
So n here, is it like the number of vertices? Or?
Yes.
So you're not, so when you said r is a constant,
Large constant.
so you're not allowing more than n?
No. So what actually happens, I just made it simple. There is a more general statement that says for every r, for every size of the badge, and then there's going to be some little more complicated expression here in the overhead. I just wanted to make it simple.
Okay.
But like you want R to be, okay, you can make it bigger, and then you'll have a better overhead, but yeah.
Should I think of a batch as a bunch of updates and then you just need to compute the value at the end? So in other words, the batch was large, you could just say, oh, let me just recompute from scratch, or do you need to actually have the correct thing at the intermediate?
No, at the end. So the batch is just, these are all the updates, then you do the calculation, at the end you have to output, at the end.
It was
There is
really
no middle.
big.
There is no middle of the batch. It just all comes at the same time.
So if it was a big enough batch, you could say, oh, let me just compute from
Absolutely.
scratch.
And that's what we actually do. Yes. Okay. This is actually not like it was just a neat trick that I wanted to show. It's not part of the okay stuff. Okay, and one more thing that's important to know about dynamic algorithms is it's important to distinguish between oblivious and adaptive adversary setting. So the way we think about this, so there is our graph G, and there is like a malicious adversary who comes and starts deleting edges and inserting edges. So in the oblivious adversary setting, the adversary needs to decide on the sequence of edge insertions and deletions before the algorithm starts. It cannot use any information it gained during this algorithm. And in the adaptive adversary setting, every time the adversary may look at what happened so far and decide which edge to update next. For example, it may look into my current spanner and decide I'm going to start deleting edges that lie in the spanner. Or it may look into the inner state of my algorithm and somehow do things that are bad for it. So generally, algorithms that can withstand adaptive adversary, they're just much stronger and more robust. So generally, we want them, it's a stronger model. But also, as I said, often algorithms for static problems, they use dynamic algorithms as subroutines. And practically in all such cases that I'm aware of, it's really important that the dynamic algorithm can withstand adaptive adversary. So it's really important to get algorithms that can withstand adaptive adversary, and so not surprisingly, this is another major direction in the area of dynamic algorithms. So one important thing to know is that if you have an algorithm that's deterministic, it always works against the adaptive adversary. You don't need to think about it, you don't need to prove anything, it's a given. If your algorithm is randomized, it may or may not work against the adaptive adversary, and you need to prove it on a case-by-case basis. But if you have an algorithm for a problem that's very basic, and you need to use it as a subroutine in other dynamic algorithms, you really want an algorithm for this problem to be deterministic. Because you want these other algorithms that use it not to have to look inside and figure out can they be adaptive update or not. So they just get it automatically if it's deterministic. So this finishes the general detour about dynamic algorithms. Now we're going back to dynamic spanners. And given all that we said, so I asked the question, what is sort of ideal algorithms for fully dynamic graphs? And here I don't really mean the best possible parameters, but like really good parameters close to the best possible, but something that doesn't look completely out of reach. So as a reminder, we're given an n-vertex graph G with lengths on edges that changes over time. And in the rest of the talk, for simplicity, I'm going to assume that all the edge lengths are 1. It doesn't make any difference in these algorithms, it's just easier to talk about it like this. And we're also given a desired stretch K. So what do we want? So first of all, we want a deterministic algorithm that maintains a spanner of G. We want the stretch to be roughly K, because K is our desired stretch. We want the size to be close to n to the 1 plus 1 over K, because this is the best size stretch trade-off. And we want very good worst case update time. So a good goal to strive for is like n to the 1 over K. This expression often comes up in all kinds of algorithms, so it's sort of a reasonable bound, and it's pretty small. So there are some additional desirable properties, and one such property is low recurse. So what's a low recurse? So every time that G changes, we add an edge or delete an edge, we may need to update the spanner H. So we may need to add edges, delete edges in H. So the biggest number of changes that H may undergo after every change to G, that's the recurse. And we want this recurse to be small, and again, n to the 1 over K is sort of a reasonable goal to strive for. So why is the recurse so important? So remember, at the end of the day, we'll use the spanner inside some other dynamic algorithm. So if we want to get a dynamic algorithm that has low worst case update time with respect to the graph G, but at the end we apply it on H, then it's really important that after every change to G, H only changes a little, because otherwise this algorithm simply doesn't have a chance. And then there are some other properties, so I decided not to go into them because then it just becomes too much, but there are some other properties that are important to various applications. So this is a lot of stuff, so I'm going to think about this first set of properties sort of a must. So when I discuss various algorithms, I'll say how they do with respect to these. And the second is just desired, so if some algorithms have these properties, I'll just mention it. So what was known about spanners and fully dynamic graphs? So first of all, oblivious adversary setting is pretty much solved. So there are algorithms that get close to the best possible stretch to size trade-off. Update time is essentially polylogarithmic. There is still some small room for improvement, but it's pretty much close to the best you can hope for. So I'm not gonna talk about oblivious adversary anymore. In the rest of this talk, we're gonna talk only about adaptive adversary. So for adaptive adversary, the high stretch regime is pretty well understood. So high stretch is logarithmic and higher. So for example, there is an algorithm that can get a polylog stretch. The size is close to linear. It's like close to the best you can hope for. And polylog amortized update time. You can also get a little worst case update time. And you will also get a little higher stretch and a little off one. So again, there is still some room for improvement, but this is very good guarantees if you're okay with a stretch that's large. And I'm just going to mention this other paper, so it gets a little worse guarantees in the update time. But the reason that I want to mention it is that this paper produces a spanner that has additional useful properties, such as low recourse and some other properties. And it is this spanner that was used in this almost linear time algorithm for max flow. And these properties were important there. So again, high stretch regime, it's sort of pretty well understood. So the question is, what happens if you want a really low stretch? So remember, stretch is the approximation factor, so generally we want it to be small. Like, for example, a constant, or like slowly growing function of n, less than logarithmic. So this was really poorly understood. Even this pretty basic question was completely open. So can we maintain for any stretch value that's sublogarithmic a spanner whose size is just a little subquadratic, so just a little less than maintaining the whole graph G? And worst case update time, or even amortized update time, I think was open, less than linear in n. So these look like really modest requests, but we didn't have any algorithm for doing that. So we resolved this question, and we sort of get close to this ideal guarantees, but not quite. So we provide a deterministic algorithm for maintaining a spanner of a fully dynamic graph. For any pair of parameters k and delta, it achieves this stretch, this size, and this worst case update time. I know it's very confusing, but the way to think about this is that, so this delta, it controls the trade-off between the stretch and the worst case update time. So for example, I can set this delta to be 1 over 100, and then the stretch size trade-off becomes basically optimal, and the worst case update time becomes like n to the 1 over 100, which is pretty low, but maybe you want smaller update time. Well, then you can set delta to be 1 over k, and then your worst case update time becomes n to the 1 over k, which is what we wanted, but then the stretch becomes exponential in k, which is not what we wanted. So bottom line, model this exponential dependence here on delta, we get basically this ideal algorithm, but if we could improve this exponential dependence to polynomial, that would be really fantastic. So our construction also has a low recourse, which is the number that we wanted, n to the 1 over k, and some other useful properties that are useful in other applications, but I won't go into it. So summary so far we discussed dynamic algorithms for spanners, and we stated our results for them. What I didn't mention is that we get similar results to a bunch of other objects, such as fault tolerance spanners, connectivity certificates, some other things. And in some of them, we get better guarantees than what was known for static algorithms. But all of these results, all of them follow from just one new technical tool that we introduced, and it's dynamic router decomposition. So in the rest of this talk, I'm going to talk about that, the dynamic router decomposition, which is the second part of the talk. So first, to provide you with some intuition, what are routers? So intuitively, routers is an attempt to adapt expanders to low distance regime. And what's a router decomposition? Is basically expander decomposition for routers. So because all of this revolves around expanders, let me tell you a little bit about expanders. So first of all, what's an expander graph? So a graph G is a phi expander. If for any partition of its vertices into two subsets, the number of edges going across this cut is at least 5 times the number of edges in the small side. And you should think about this phi as being either a constant between 0 and 1 or something like 1 over polylog n. So obviously, if a graph is not an expander, then there is some cut that violates this property, and we call it a sparse cut. And even if it violates the property approximately, I'm going to call it a sparse cut. So expanders have become one of the most powerful and useful and often used tools in the design of algorithms for graph problems. And one of the really neat properties of expanders that makes them really useful is that any reasonable demand on expander can be routed on shared paths under slow congestion. So let me decipher this. So we can think about the demand as just a bunch of pairs of vertices in a graph, SITI. And then a routing of this demand is when we connect every pair SITI with a path, and we want the length of the path to be at most polylog n, and we want every edge in this graph to participate in at most polylog n such path. That's a quotation. So more generally, we can think about the demand as specifying for each one of these SITI pairs also the demand amount Ti, and this is how much flow I want to send from Si to Ti. And now a routing is for every I, we need to send Ti flow units from Si to Ti. We want this flow path to have only polylogarithmic lengths. And we want every edge to carry the most polylog n flow. That's again the condition. So in expanders, any reasonable demand can be routed like this. What's a reasonable demand is something we'll call degree-bounded demand. So we require that for every vertex V, if we look at all the demand pairs in which it participates, the sum of these demands is at most the degree of this vertex. It's like very reasonable, right? So this is the central property of expanders that makes them very useful, and now how they're usually used. So suppose we want to solve some problem on a general graph. What we can do is first reduce it to the same problem on expanders, and then solve on expanders, and often it's easier because of this property or some other good properties that expanders have. But how do we reduce a problem from a general graph to that on expanders? So one of the main tools for doing this is called expander decomposition. This is when we take our graph, input graph, and we break it into subgraphs that we call clusters, so that every cluster is an expander, and there are only a few edges connecting different clusters. So if you want to carry out this plan, we need to have a fast algorithm for computing this expander decomposition. So the first such algorithm was suggested in this famous paper of Spielman and Tang. The running time of the algorithm is very good, it's close to linear in the size of the graph, but it doesn't really compute an expander decomposition. So the clusters in this decomposition, they're not really expanders. They sort of behave like expanders in the context of the entire graph. So what does it mean? So if somebody gives me degree-bounded demands inside each one of these clusters, you can route all of them simultaneously through short paths, low congestion, everything like you wanted. But the routing is not contained in the cluster. So the routing for a single cluster, it can go outside of the cluster and use vertices and edges from various other clusters. So this was a really big result. It led to many algorithmic developments. But some of these algorithms were probably more complicated than they needed to be because they use this not quite expander decomposition. And also there are some settings where you do need the proper expander decomposition. So this was remedied in this paper of Saranurek and Wang, which is also like really remarkable paper. And they gave a close to linear time randomized algorithms for actually computing a proper expander decomposition. So every cluster in the decomposition is actually an expander. And this led to a huge number of new results. Like there are so many, like I think almost like many algorithms in recent years for graphs, both in static and dynamic graphs, use this. And also it led to simplification of some of the old results that use this not quite proper decomposition. And I'm just going to mention that there is some recent work on also getting deterministic algorithms for expander decomposition. And also there has been some work about expander decomposition in dynamic graphs. And this in turn is used in many dynamic algorithms. In particular, the previous work that I mentioned on spanners, it uses dynamic expander decomposition. Okay, so now I'm going to do a second quick detour. And so what I want to talk about is the tools that are used to get fast expander decomposition. Even though it's not the main topic of this talk, what's going to happen is that later we're going to define routers, which are equivalents of expanders, and router decomposition, which is equivalent of expander decomposition, and some of these parallel tools that I want to connect to. So suppose this is my graph G, and I want to get a fast algorithm for decomposing it into expanders. So how would I do it? There is a pretty simple idea. Suppose somebody gives me a fast algorithm that given G either certifies that G is an expander or computes a sparse cut in G. Well, in the first case, I'm happy. The expander decomposition is just G itself. And in the second case, I get these two new clusters with few edges connecting them. I can recurse on them, and I'm done. And in the end, I'll get expander decomposition. And the really great news is that such a subroutine does exist. It's called the cut matching game of conduct around with Rani, and it's very fast. The time is close to linear in the number of edges. So I just want to quickly say a few words about this cut matching game, and in particular, how can we certify that our graph is an expander? So here's the idea.
So do you need this to be balanced somehow?
Yeah, we'll talk about this.
Okay.
Good catch, very good catch, yeah. Yeah, so how can I certify that G is an expander? So here is how. I can build another graph on the same number of vertices, which is known to be an expander. For example, I can use existing construction, or I can specifically construct it so that it is an expander. And then I can try to embed it into G by mapping every vertex of this graph to a distinct vertex in G, and every edge to a path connecting the correct endpoints of the edge. So this is the right edge, the right path. So maybe this is the embedding, and I want to make sure that the congestion of this embedding is small, so every edge of G participates in few embedding paths. If I can do this, then this is a proof that G is an expander itself. A little worse, but still an expander. So this graph X together with embedding is a certificate that G is an expander. So what the cut matching actually does, the cut matching game, and this is roughly speaking, this is not precise, given a graph G, it either builds such a certificate for G, or it produces a sparse cut in G. So going back to expander.
Sorry, where in X you take to be a fixed expander?
It's actually built, the construction of this expander is done in parallel with embedding and is sort of guided by the embedding, but it doesn't matter.
Okay, so you find that, but what you find is both X and an embedding.
Yes, at the same time, yeah. But it doesn't matter, you can maybe do other things. In that cut matching game, this is how it's done. Okay, so we do have a subroutine like that, so are we done? As Nati very wisely noticed, no. Because this procedure actually does not lead to efficient algorithm. So let's see why. So in the first iteration, we already invested omega of m time, like the size of G. And we computed this sparse cut. Now, if the sparse cut is roughly balanced, so each one of the sides roughly contains, let's say, half of the edges of G, then we are happy, because then we got to cluster that is significantly smaller and we can continue. But what happens if this cut is very lopsided? So for example, A is much smaller than B. In this case, we may be in trouble, because again, we invested omega of m time, and all we did, we took out a small piece out of G. So this is now B, right? And then in the next iteration, maybe we again invest omega of m time, and we again take out a small piece of B, and of G, and so on. And so in the end, we can have a huge number of such iterations, and every iteration we invest a lot of time, and this does not really give us sufficient algorithm. So one thing to note is that if the cut matching game returns a cut that's very unbalanced, it actually guarantees that there is no sparse balanced cut. And from here, one can infer that B itself is close to being an expander in several different senses. But for example, one can add just a small number of edges and vertices to B and turn it into an expander. Of course, I'm not allowed to add edges and vertices. I want to cut my existing graph. But the question is, in a situation like that where B is very close to being an expander, can I very quickly recover a large subgraph of B that's an expander so that I don't have to recurse on B, and then I can recurse on the rest? So it turns out that we can. An essential tool that is used for this is expander pruning, which is a really cool tool, and it's interesting in its own right, and is used in all kinds of places. So now I'm going to define this expander pruning, and it's like completely abstract thing, not connected to what we did so far. So in this expander pruning, we're given a graph that's initially an expander, and then an adversary comes and starts deleting edges from this graph one by one. So maybe this is the first edge that the adversary deletes. Now, once an edge is deleted from this graph, maybe it stops being an expander. So our goal is to turn it back into an expander. And to do this, we're allowed to delete some vertices and their incident edges from the graph. So in every iteration, adversary deletes one edge. We need to prune this graph by deleting some vertices, turn it back into expander. So Saran-Arakan, so maybe these are the vertices we prune out. So Saran-Arakan one produced, they gave a really cool algorithm for this problem. So the running time is close to linear in the number of edges that the adversary deletes. And the number of extra edges that our algorithm deletes is also very close to proportional to the number of edges that the adversary deletes. So we don't delete that many extra edges. So without going into too much detail, in a situation like that, where we got a very lopsided cut, and we know that B is almost an expander, one can actually use this expander pruning in order to recover a large subgraph of B that's an expander, and then you recurse on the less. So to summarize, what are the central tools for expander decomposition? First one is a certificate that the graph is an expander. A certificate is another expander that's embedded into a graph with low congestion. And second one is expander pruning. So when combined with the cut matching game, this gives a very fast algorithm for computing expander decomposition. But in fact, also if we want to maintain expander decomposition in a dynamic graph, then you use these tools and maybe with a little bit of work. This is how it's done today. So this finishes the detour into expander decomposition, and so far we talked about all the good things, expanders, and now we're going to talk about bad things. So we said one of the important properties of expanders that makes them useful is this routing, that any reasonable demand, you can route on paths of at most polylog n lengths with at most polylog n condition. But what happens if I need a routing on much shorter paths? Well, of course I need to choose demand pairs so that they're close to each other. But even if I choose demand pairs that are very close to each other, and I just want some non-trivial congestion, expanders can give me anything shorter than polylogarithmic path length. So if you're using expanders, you're pretty much doomed to use paths of polylogarithmic lengths. And because of these reasons, often when you use expanders in distance-based problems, you immediately lose at least polylog n factor on the approximation factor or on the stretch. And in fact, this is the reason why the previous algorithms for spanners, they lost this polylog n factor in the stretch. They were in the high stretch regime. So if you want to do a small approximation factor or a better stretch, you should do something different. So motivated by this, several papers introduced several objects whose goal was to replace expanders in the setting. I don't want to go into these objects and what are exactly the connection between them. That's not important. The important thing is that by now I think we're converged on the right object, and this object is the router. So that's what I'm going to talk about now. So what's a router graph? So a graph is a DC router if every degree-bounded demand can be routed inside this graph on paths of length at most d and with congestion at most c. So for intuition, typically, we are given as input some parameter k that is usually like a large constant or a slowly growing function of m. And then we want d, the length of the routing path, to be at most poly k, and the congestion to be at most n to the 1 over k. For comparison, in expanders, we get d polylog n and congestion polylog n. So what happens here is that we want to get much shorter paths at the expense of a little higher congestion. Now, what's a router decomposition? It's like expanded decomposition only for routers. So we want to compute a collection of clusters of the input graph G so that each cluster is a router. And we want to make sure that almost every edge or even every edge in our graph lies in some cluster. And we no longer require that the clusters are disjoint. This seems too hard, but we require that every vertex only lies in a small number of these clusters. And this previous work produced very fast algorithms for maintaining a decomposition of a dynamic graph into almost routers. So again, the clusters in this decomposition, they're not actually routers. They sort of act like routers in the context of the entire graph, in the same spirit as the almost expanded decomposition of a Spielmann tank. So if we're given degree-bounded demands in each cluster, we can route them, all of them simultaneously on short paths with low congestion like we wanted, but the routing paths are not contained in the clusters, they may go outside and visit other clusters. Finally, we got to our main result. So our main technical result is a deterministic algorithm for fully dynamic graphs for maintaining a router decomposition. So the input is a fully dynamic n-vertex graph G and two parameters k and delta. And the algorithm maintains a collection of clusters or subgraphs of G. Each one of these clusters is a router, so any degree bounded demand inside the cluster can be routed on paths of this length and this congestion inside the cluster itself. Every vertex on average lies only in a small number of the clusters, and almost every edge or even every edge of G is in some cluster. This depends on some parameter setting.
Put a bit less into this.
Okay, yeah. And this is the worst case update time. Again, a little confusing. The important thing here is that this delta, it controls the trade-off between update time and this length of the routing path, and it does not influence anything else. So additionally, we do on-the-fly sparsification of the clusters. So I don't want to bore you with too many technical details. I'm just going to say that for each one of these clusters, we also maintain a sparse subgraph of this cluster that in itself is a strong enough router, without going into specific details. And lastly, we maintain a graph H, which is a union of all these sparsified clusters, and also the edges that don't lie in any cluster. And this graph is a dynamic graph, and it has a low regress. The bottom line from all this is that we can actually use this H as a spanner, and we can show that it has all the required properties. And more than required properties, it has even extra. You can use it as a fault-tolerant spanner, as connectivity certificate, and all kinds of other things. All of them just follow from this one decomposition theorem. And some of these new results, they crucially rely on the fact that this decomposition is proper, but also we saw that generally it feels like proper router decomposition just appears to be a clean and a more useful tool than this improper one, sort of in the spirit that's what happened with expanders. So now I'm going to very quickly mention some technical ingredients that go into this decomposition at a very high level. So the first ingredient is the explicit construction of nice and simple routers with superscript density. Actually, this construction just slightly generalizes a similar construction from a previous paper, but it's generalized so that on the one hand, we can make these routers with any density that we want, and on the other hand, it's very easy to sparsify them. And then these explicit routers, they can be used as a router certificate, similarly to what we did with expanders. So if this is my cluster and I want to certify that it's a router, I just build this one explicit router on the same set of vertices and embed it into this cluster through a short path that calls low congestion, and together this is a certificate that this cluster is a router. Also, we provide efficient algorithm for pruning these routers. This is the analog of the expander pruning. And it's a little more complicated than the pruning algorithm from this previous paper, but it gets a better stretch to time trade-off. And lastly, we provide a fast algorithm that, given a cluster C, either constructs a router certificate for a large subgraph of the C, or it deletes a few edges from the C and breaks it into smaller subgraphs that are also clusters, so that they have very small overlap, and each one of these new clusters has much fewer vertices. So the idea here is that we can now use this algorithm in this scheme that we used for expander decomposition. So it just replaces this cut matching game and pruning, and then you just use the same scheme to compute the router decomposition. And lastly, in the last 2 minutes, I just want to quickly mention a technical challenge that comes from trying to maintain a proper router decomposition. So suppose this is one of the clusters in the decomposition, and suppose I have computed a good certificate for this cluster. So I computed this explicit router on the same set of vertices, embedded it into C through shared paths that cause low congestion, everything is good, it's a certificate, it sees a router. But remember, graph G, it undergoes updates, right? So adversary may come and delete some edge that sits in this cluster C. And now, when this edge is deleted, the the routing path cannot, the embedding path cannot use it because it's gone, right? So I need to go back into this explicit router and I have to delete every edge whose embedding path uses this edge E. Now I deleted some edges from this router, maybe it now stopped being a router, and I want it to be a proper certificate, it needs to be a router, so I have to prune it. So maybe I prune it and delete these vertices and turn it back into a router. But now the vertices that I pruned out, they're still in C, and the certificate doesn't capture them anymore. So I have to take them out of C, because I need to have a proper certificate for C being a router. So I take them out of C, and maybe I put them in a different cluster. But now we have a problem again, and the problem is that some of the edges of this RC, their embedding paths may still use these vertices that they took out. Okay, now I have to go back and delete these edges again. Then I need to prune again, then I need to take vertices out. And it's just not clear how this process can terminate in any reasonable way. So the way we get around it is that we use a different router certificate. We don't require that this RC contains all vertices of C. We only require that every vertex of C participates in a large enough number of embedding paths. And it turns out that this is enough to ensure that C is indeed a router. And now, even as we prune this RC, we don't have to immediately delete these vertices from C, and this makes a difference. But eventually, you still need to design a pruning algorithm for these kind of routers, like this C, that have this kind of certificates, and this is quite a bit of work. So, to summarize, we obtained the first adaptive update and, in fact, deterministic algorithm for maintaining spanners in dynamic graphs. I won't go into these parameters again. I'm just going to say that the one thing that is really annoying is this trade-off between the update time and the stretch. And if we could replace this exponential in delta with polynomial, it would have been much, much nicer. And the same construction also gets fault-tolerant spanners and all kinds of other things I didn't talk about. And all of these results follow from one construction of a deterministic algorithm for maintaining a proper router decomposition of a fully dynamic graph. We also maintain a sparsified router for each one of the clusters and all these other things that I'm not going to read. So that's all. Thank you.
Questions?
So, does your algorithm have better amortized guarantees, or the amortized time is same as the worst case time? It's the same. One more question I had was so your algorithm has a polynomial update time. Is it sort of something fundamental for this problem? Can we expect in logarithmic?
No, it's n to the 1 over k, right? So if k is a slowly growing function of n, it's not polynomial. It's actually n to that doesn't matter. No, there is no reason why you can't. I mean, it's n to the 1 over k is sort of reasonable, especially if you go through batch update model where this kind of thing also sort of arises, though maybe you can make a bigger R there, this expression always arises in these problems, it sort of makes sense.
Okay, so do you ever, do you think of k, I know that k was less than log n is the regime you were considering, but k constant, is that also interesting? So I was thinking of polynomial time in terms of just k being constant.
No, absolutely. In fact, many people look at k equals to 2, k equals to 3, and try to nail these regions down, yeah.
Okay.
So we were more like k biggish constant.
Actually, sorry, so just following up there, because also curious. So for k that's 2, or even k that's 7, or something like that, is any k is constant k. Is this an improvement, or then other methods are?
No, I don't think so.
And I'm curious how.
I mean, we get stretch that's poly k times 2 to the O delta, right? We are not getting a small stretch.
And I'm curious, how implementable are these? So how is it? Because you started. The near expander methods and methods based on them, those are actually implementable. So.
Yeah, good question. Yeah. But those are sort of specifically designed to be implementable. We're not there yet.
So is it?
No. I also don't know of any people who want to implement. If you find them, I'll think about it.
So you want to implement?
Algorithms for spanners.
That I think. I don't know them personally. Maybe.
Okay.
Other questions?
For k equals 2, what is the best one could reasonably hope for? So there,
I mean, the size of the spanner itself is going to be n to the 3/2 or something like that, right? I mean, there are some papers that get some results, I don't remember what they are. But they're not like very fast algorithms.
Okay. Okay, let's thank Julia again.